Welcome to section 3.4, classification of the states. So here we want to understand the structure of the state space. Recall from the last section where we dealt with recurrence and transience that we looked at one state and we decided whether it was recurrent or transient according to the n-step transition probabilities. But this was really for one state. Yeah, sometimes we could argue, well, all the states look the same, so this has to be the same. But if you have one Markov chain where all the states have a slightly different function, then how do you relate the recurrence of one state to, well, recurrence or transience of states that are close by? And that's the aim of this section. So here you see an example of a Markov chain again. So there's 4 states. And some of the states have interesting other functions, basically. So we want to get to know new notions and really mathematically describe what is going on. So for example, the state 3, if you look there, then this state is absorbing, and we will define what this is also technically. But heuristically, I think it's clear what is meant. So if you are at 3, then you stay at 3 forever. Yeah, so you'll not be able to return to 2. And anyway, even if you are at 2, you're not allowed to go to state 0 or state 1. Yeah, so in mathematical terms, we will define what it means that a state is reachable. One state is reachable from another state, or if states communicate. Yeah, and we will define what are communicating classes. You see that, well, you can guess that this Markov chain consists of at least 2 communicating classes. Yeah, the 0 and 1 is a communicating class, and actually 3, only the 3 is a communicating class. Yeah, the state 2 is something that is insignificant because I may start at 2 and I may stay there for a while, but eventually I'll go to state 3 and then I can forget about the state 2. Yeah, it's insignificant for at least for the long time behavior of the Markov chain. Yeah, so we are going to define these terms and prove different relations, and in particular consider the phenomena of recurrence and transience and how they relate to these notions. I would like to start this section by defining some auxiliary concepts, and with the help of these we can formulate the new definitions of the new terms that you already saw in the introduction. The first concept is the kth return time. So we start with the state j. We define the 0th return time as 0. And then we define the kth return time as the minimum of the times after the k minus 1th return time, such that xn visits j. So you have to imagine it this way. Assume we are starting at j. So at time 0, R0 is 0. Now we start at j. Of course, I didn't assume this, but you will see that in the next definition this will be assumed. So we start at j, and then we move away from j, and then we return to j, and we call this time R1. Yeah, and then we move a little bit away from j, and we return to j at R2, and so on. Okay? There are 2 issues with this definition. One is that we call this return time, and well, I marked this here also in the picture as returning to j because we start at j, but I didn't assume this. But as I said in the next definitions, this will be assumed. So if it's not a return time, then it's sort of R1. So if you start elsewhere, R1 is sort of the first hitting time of state j. Okay, and otherwise it's the first return time to j. The second issue is that it may be that you never return to j. So let's say this is your last return time to j, and then you don't return to j. Then we're going to put all the other r's to be equal to infinity. So let's call this rk. This is still finite, but rk k plus 1 is plus infinity. And this can be achieved with the convention that the minimum of the empty set is plus infinity. Yeah, so if there is no time when you return to j, then you put this minimum to be equal to infinity. Furthermore, we need the following notation. We call the differences between the r's t. So tk is rk minus 1. Yeah, so this first thing here this is T1. I leave off the J because we fixed the state J anyway. And this is T2. And this difference is T3, and so on. Yeah, so these are the times between the visits to J, and you can call this the length of the excursion away from J. I already mentioned that we want to consider these random variables whenever we start from J, so assume that we start at J. Furthermore, consider the case that the state J is recurrent, so that almost surely you do return to J. And it's a homework then to show that these Rk and Tk are well-defined, almost surely finite random variables. Yeah? And most importantly, that the Tk, so the times between the visits at J, that they are independent and identically distributed. So that's quite an important fact, and it justifies this heuristics that I've been talking about in the last section, that you start from J, you make an excursion, and then you basically start anew, start afresh from J. And here the Tk are the lengths of the excursions, and as you see, what you should show is that they are independent and identically distributed. Yeah? So you return to J, and then you forget everything that you have been done so far with your Markov chain, and you start a new excursion which has the same distribution as the excursion before. So now we are ready to introduce the terms that you already saw in the introduction. The first thing we define is for a recurrent state J, we call that state positive recurrent if the expected T1, so T1 is equal to R1, so the expected return time, first return time, is finite. Notice that we can reformulate recurrent with the help of the T's or the R's. So recurrent means that Tj1 is finite, Pj almost surely. So T1 is the same as R1 because, R0 is 0. So this says that the first return time to J is finite when I start at J. And now you see the difference to positive recurrent. Positive recurrent is that not only the random variable is finite, but the expectation of this random variable is finite. Yeah, so that's demanding more. So it's a stronger form of recurrence. If J is recurrent, but not positive recurrent, it's called null recurrent. So this was still a definition concerning one state only. Now we want to communicate between the states or jump from one state to another. And we say that state J is reachable from state I, and we write I arrow J, meaning I can make it from I to J, if there is an n such that the n-step transition probability from I to J is positive. Yeah. Recall that this was the probability that starting at I, xn is J. Yeah, so I start at I, and there is an n such that with positive probability I reach J. So this is going to help us exploring the neighborhood of I. Yeah, so you start at I, and then you ask, well, what other states are reachable from I? Yeah. So you start at I, and then you try to see what is reachable. So there is a J reachable, but possibly others. Maybe a state K is not reachable. Yeah. If we can reach J from I and I from J, then we say that I and J communicate, and we write I double arrow J. Note that clearly there may be situations like this one where you can reach 2 from 1, but not the other way around. Yeah. So in this case, 2 and 1 do not communicate. The last term I want to define here is when a state is called absorbing, and the formal definition is as follows. So for any I that can be reached from J, I has to be equal to J. So the only place I can reach from J is J itself. Yeah? So think of this example here. So the state 2 here, if I'm there, if I can reach something, then the something must be 2. Yeah? I cannot go elsewhere. Here's an exercise. So this is the Markov chain that you already saw in the introduction, and we now defined mathematically correct what it means to be able to reach from one state to the other, or when two states communicate, and when a state is absorbing. So please stop the video here and try to think in this example what these notions mean. Yeah, so between 1 and 0, are they communicating, and so on. So try to look at pairs of states, see if they communicate, see if the states are absorbing, and so on. Okay? Here comes my solution. So I hope you practiced these new terms. So I've written up the solution here. So clearly 0 and 1 are communicating. Yeah, you can reach 0 from 1, and you can reach 1 from 0. Yeah, and you can also reach 0 from 0. You can reach 1 from 1, and you can reach 3 from 2. Yeah, you can walk from 2 to 3, and you can go from 2 to 2, and you can go from 3 to 3, and 3 is absorbing. Yeah, and 2 and 3 don't communicate because you cannot go from 3 to 2. Okay, so I guess these terms are more or less intuitive. So let's introduce some more terms. And the first notion is the one of communicating class. And you can already see somehow that things like this here are supposed to be communicating classes. Yeah, so you can go from each state there to each other state, and you don't miss anything where you can go. Yeah, that will be the definition of a communicating class. So the formal definition is as follows: a set S, non-empty, subset S of E is called communicating class if, first of all, I and j communicate for any combination of I and j from S. The second property says that you should not exclude any states that you can reach from the states in your communicating class. Yeah, so if you have a state I in your communicating class, and if you have another state somewhere of the Markov chain, and you can reach that state, so you can reach j from I, then j also has to be in the communicating class. The second definition is as follows. So a state j is called significant if there is a communicating class containing j. Otherwise, the state is called insignificant. So you can already take a look here into this example and see if you possibly find any state that is insignificant. If not, this will be formulated as an exercise immediately. Before we do that, let's finish this definition. So the last thing that is defined here is that if E is a communicating class itself, so if the whole state space of the Markov chain is a communicating class, then the Markov chain is called irreducible. So think of this notion as, well, if the Markov chain consists of a few communicating classes, then you can sort of concentrate on one of the communicating classes and do all the stuff in there. Yeah, because anyway, I cannot reach from here to there. Yeah? And the Markov chain is irreducible, so you cannot further split it, sort of. You cannot further split the state space if it consists only of one communicating class. It's always very good to understand new notions with the help of examples. So please have a look at the example on the top of the page and then try to find communicating classes there. Try to see if there are insignificant states and try to think of whether the whole Markov chain is irreducible. Yeah? So please stop the video here and try to check these new notions with the help of the example. Here comes my solution. I think the easy communicating class is this one, right? because, well, you can reach from 0 to 1, from 1 to 0, and you cannot reach any other state from these two. Yeah. So this is a communicating class. Yeah, the set is with 0 and 1. The second piece of the Markov chain topology is a little bit more tricky. So certainly 3 itself, just a set with a 3 in it, is a communicating class, because you can reach 3 from 3 and you cannot reach elsewhere. Yeah? So S2, the second communicating class, is 3. And as you can see here, 2 is not part of any communicating class, because, well, there are no states that lead to 2. Yeah? So 2 is not part of any communicating class, so 2 is insignificant. So I've written it up this way: S1, S2 are communicating classes, 2 is insignificant. And the last question is the Markov chain irreducible? And the answer is no, yeah, because they're, well, E is not a communicating class. Yeah, you have 2 communicating classes, so no. And additionally, you have insignificant states, so certainly the Markov chain is not irreducible. So I hope this clarifies this notion again, irreducible. I mean, you can look at this communicating class and you can do, you can ask questions here, and you can look at this communicating class and ask questions here. Certainly they are not very interesting. And you can forget about the insignificant state, because sooner or later, anyway, I will go from the insignificant state into a communicating class, and then I can forget about the state. So basically you can reduce the analysis to, well, either the communicating class S1 or the communicating class S2. Yeah? We can now formulate the main theorem of this section, and this says the following: if a state I is recurrent, and I can move from I to J, so J is reachable from I, then J is recurrent, and I and J communicate. So how do you imagine this? Well, the state I is recurrent, so whenever you start at I, you will return to I eventually, and you can reach J from I. So there is a way of getting to J. Yeah, then J also has to be recurrent, and you can get back to I. And the heuristic reason for this theorem is that, well, whenever you start at I, if you go to J, this cannot be a dead end. Yeah? If it was a dead end, then there would be a possibility of leaving from I and not returning. Yeah, but I is recurrent, so even if you walk over J, you will eventually go back to I. And if you can basically start from J and go to I, there is a way from I to J. Yeah, so this is very heuristically the idea behind the proof of this theorem. We can draw the following corollary from this theorem, and the corollary says that all states of a communicating class are either all recurrent or all transient. Why is that? Well, if you have a communicating class and I is in your communicating class and I is recurrent, then you can reach all the states J in your communicating class from I. Yeah, and the theorem then says, well, all the states, well, the state J is recurrent, so all the other states in your communicating class are recurrent. How about the case when the communicating class is transient? Well, let's start with the case that one I is transient. Then assume that there is a J in the communicating class. Let's call this S, so I in S, and S is a communicating class. And the J is recurrent. So assume there are transient and recurrent states in your communicating class. Then, since it's a communicating class, I is reachable from J. Yeah, and J is recurrent, I is reachable from J. By the theorem, I also has to be recurrent. Yeah, so I cannot be transient. Yeah, you cannot have transient and recurrent states in one communicating class. Or in other words, all the states in one communicating class are either transient or recurrent. Let's start with the proof of theorem 329. The proof follows the heuristics that I sketched after the theorem. So I is recurrent, I can reach j from I, and while we want to show that, first of all, that j is not a dead end, yeah, and that I can go back from j to I, yeah, that would be the first part that we show, and we assume that this is not the case. So assume that one cannot reach I from j, yeah, that basically j is a dead end. So we will use this assumption at a place which I indicate by star, and you will see at the bottom of the page that this leads to a contradiction. First of all, since j is reachable from I, we can find a k such that pijk is positive. Yeah, this is the definition of j is reachable from I. And I mark this property double star because in the following computation I'm going to use it at the place marked double star. Here comes the computation. So the first thing we are using is that I is recurrent. If I is recurrent, it follows that you see I infinitely often. So you visit I infinitely often. Yeah? The probability that xn equals I infinitely often is 1. So the probability of the complement is 0. Yeah? So this is the recurrence of I. In other words, I start at I and I see xn equal to I only finitely many times. Now, what is a possible scenario for this event here, for seeing I only a finite number of times? Well, one possibility is we have to start in I, and then at time k we reach j, and after time k we don't visit I anymore. Yeah? So there is a time k, yeah, which I'm fixing, and k is the k from here, and at time k you visit j, and after that you don't see I anymore. Yeah? There are certainly other possibilities of seeing I only finitely many times, but this is one possibility. Yeah? So in particular this event here, this implies that I see the state I only finitely many times. Now, for technical reasons, I'm writing the ... as the limit, capital N tending to infinity, of the probability that I start in I, well, I start at I, at time k I visit j, and then I don't see I up to time n, yeah, capital N, and n tends to infinity. So this is just the property of the probability measure of continuity from above. Yeah? So these sets here, if I call these sets an, these sets are decreasing in n, so the limit of the probability of decreasing sets is the probability of the intersection, and the intersection of all the an is the event that is in here. Yeah? So this is by continuity from above of the probability measure pi. The next step is to introduce a conditioning. So I'm going to condition on xk being equal to j. Yeah, if I do that, well, I should put a comma here, I should put an and here, then it would be the same as the line on top. But I'm putting a conditioning here, and it means that I'm dividing by the probability that xk equals j, and I have to multiply by this probability in order to not make any mistake. So this step was just multiplying and dividing by the same factor, namely this one, and then writing the second part here as a conditional probability. The next step is exercise 310, which says the following. You have whatever initial distribution. If you condition at time k to be at a specific place, here at the place j, and then after time k you put whatever conditions, then it's the same as starting from j and then having these conditions that you see here, but at the shifted Markov chain, basically. Yeah, so I'm going to subtract k from each of the times here. So I'm going to subtract k here, and also here, which means I have to subtract k from n, and also here, so this becomes a 0. Yeah, and this is what you see in the next line. So you start at time 0, you start at j, which is this blue j here. Yeah, this comes from the blue j here. these conditions, well, they are modified in the sense that I subtracted the k everywhere. And I forgot about this I because I can write here any initial condition. Yeah, this is what exercise 310 is about. The next step is to move this limit n tending to infinity back into this probability here. And the justification is the same as above. So this here is set, say, bn now, and the bn are decreasing. I'm taking the limit of probabilities of decreasing sets, which by continuity from above of the probability measure is the probability of the intersection of the bn, and the intersection of the bn is written here with a dot, dot, dot. And of course, this first term here is just copied to the next line. Yeah, it doesn't depend on capital N. Now I'm using the star and the double star from the beginning here. So the star is used to see that this probability here is 1. I start at j and I never visit I. Yeah, this has probability 1 by this assumption here, because from state j I cannot reach I. Yeah, the Markov chain cannot be at I if it starts in j. Yeah, so it starts in j and it never reaches I. This has to have probability 1 by star. Furthermore, this first term here is just, rewritten. So this is the k-step probability to get from I to j. Yeah, you start in I, and at time k you want to be at j. So this is pijk, yeah, by definition of this notation. And by double star, this quantity here is strictly positive. Yeah, this was our assumption that you can get from I to j. Yeah, we chose the k in such a way that pijk is strictly positive. And this gives us a contradiction. Yeah, we started at 0 and then we estimated, and we saw that this quantity here is strictly positive, and this, of course, must not happen. And this gives us a contradiction, because here we started at 0, we estimated, and then we estimated against a term that is strictly positive. Yeah, this cannot be true. This is a contradiction. So our assumption that you cannot reach I from j has to be false. Yeah, so we must have j, you can reach I from j. And since you can reach I from j and j from I, we know that I and j communicate. Yeah, so this part is already proved. And it remains to be seen that j is recurrent. And this is the purpose of the second page of the proof. So step 2 is to show that j is also recurrent. Since j can be reached from I, and we just showed that I can be reached from j, we know that there are n and m such that pjin is positive and pijm is positive. Yeah, that's the definition of reachability. Yeah? J can be reached from I and I can be reached from j. Now comes another computation. So we are going to look at pjjn plus r plus m. And the reason we are considering this is that we are going to sum over r in this case. And we want to show that this sum in R is infinite. And if this sum is infinite, then we will see that j has to be recurrent. Yeah? And of course, we're going to use on the way that I is recurrent. So what is this strange thing, pjjn plus r plus m? Well, it's the probability starting in j that you reach j at time n plus r plus m. Yeah? This is the definition of the symbol on the left. We're going to consider again a scenario how you can be at time n plus r plus m at j. Well, I'm just going to insert additional conditions here. So at time n, I wish to be at I. At time n plus r, I wish to be at I. And of course, at time n plus r plus m, I would like to be at j. So this is simply the monotonicity of the probability measure. Yeah? I've inserted these two conditions. And then, of course, I'm making the probability smaller. The next step is to introduce a conditioning. And I'm going to condition on xn being I. Yeah, this appeared here together with the other two conditions, and I'm going to write the two conditions here, and I'm going to condition or take the conditional probability on this xn being equal to I, which means I've divided by the probability that xn equals I, so I have to multiply with that probability, yeah, in order to not make any mistake. Notice that when we divide by the probability of this event, we have to take care that this probability might be 0. Yeah? Actually, we will see that this probability is pji to the n, which is positive, so it's never 0. But even if it were, then this term here is 0, and we are going to see this term in the final estimate, and it will multiply whatever is behind it, and then this estimate is also correct if this term here is 0. Yeah, because, well, the left-hand side is certainly greater or equal 0. Yeah, so there's no issue here whenever this term might be 0. The next step is again exercise 310, here applied to the second term. So exercise 310 says the following: whatever is the initial distribution, here the initial distribution is that I necessarily start at j, but whatever is the initial distribution, if I condition the Markov chain to be at state I at time n, then you have some conditions after that. It's the same as if you start the Markov chain at time 0 at I, and then you require these conditions here, but you require them not at xn plus r, but at xr, and then here also. So I'm going to subtract the n here, yeah, and move all this into 0, yeah, because the Markov chain basically starts afresh here at time n, so it's the same as starting at time 0 at I, and then doing what it's supposed to do. The next step is essentially the same business. So if you look at this term here, so it contains a condition xr being equal to I. I'm going to condition on this, which means I divide by the probability that xr equals I. So I have to multiply again by the probability that xr equals I, and then I get this conditional probability here. And here there's the same issue with this term possibly being 0, and we argue as above. So if this term is 0, this term will appear in the final estimate. So whatever we do afterwards and whatever it multiplies, it will give 0, and the estimate will be trivially true. And then again, I'm going to use exercise 310, which says that whatever is your initial condition, yeah, so you can forget about this initial condition or initial distribution. If at time r you want to start from I and you want to do something after r, it's the same as starting at 0 at I, yeah, which is here, and then subtracting here the r from the time indices after the start of the Markov chain. Yeah, so this is again exercise 3.10. Now let's translate these probabilities into the n-step transition probability language. So the first one is that you start at j, and at time n you want to be at I. So it's pjin. The second one is that you start at I, and at time r you want to be at I. So it's piir. And the last one here is that you start at I, and at time m you want to be at j. So this is pijm. Okay, and I marked this inequality here because we're going to use this quite a few times later on also. Yeah, so this is quite an important proof in a sense, because it will appear as a piece of other proofs later on. Yeah, so I will put a remark after the proof saying that inequality plus will be used later on, and I will put a number to it in order to be able to reference it. However, in this proof we're going to sum in R. Yeah, I already announced this before we started the computation. So we want to sum up this thing here in R, and what we get is the sum in R, pjj of n plus r plus m. So this thing is greater or equal the sum of the right-hand side in plus. Yeah. And on this right-hand side, we can move these two quantities out of the sum because they have nothing to do with the r. Yeah, so we move them in front of the sum. And then we carefully look at these three quantities. So this one here is positive because it's set here, yeah, by construction, by the choice of n basically. This thing here is also positive by the choice of m. And this thing here is plus infinity because I is recurrent. Yeah, so here I use that I is recurrent. Yeah, this is the place. So this means that the right-hand side is infinity, so the left-hand side also has to be infinity. And the sum here on the left-hand side, which is infinity, as we just found out, is a part of the sum that you see here. Yeah, here you sum up the pjj starting from n plus 1 plus m. Here you sum up the pjj starting from n equal 1. Yeah, and if this part starting from n plus 1 plus m is plus infinity, then of course this full sum will also be plus infinity. And by the recurrence transience criterion, this shows that j is recurrent. And this is what was left to show in this proof, and we are finished with the proof. As already mentioned in the derivation, I would like to keep this inequality plus here for later use. So I'm going to note down this inequality here. So for any nmr times and states ij, this inequality here holds. And yeah, this will be remark 331, and actually we're going to use this excessively. And I would like to mention also that we do not need any extra conditions for this plus here. So formally we had these positivity conditions here, but in the derivation of this inequality we did not use it. Yeah, actually we did use it at some places, but if one of these positivity conditions is false, then the right-hand side is 0, and then the inequality also holds. Okay, so this inequality here holds for really for all times nmr and all states ij. There's one last corollary that I would like to present, which I think looks quite nice. So it says, if a state is recurrent, then it is significant. And the proof is an exercise. So please stop the video and try to prove this. And if you continue with the video, you will see my solution. Okay, so my solution goes as follows. I'm going to define the following set. I'm going to define the set of all states j in E such that you can reach j from I. And I'm going to claim that S is a communicating class and that I is an S. And if that's true, then I is part of a communicating class and I is significant. So first of all, notice that I is an S because I is recurrent. Yeah? Because I is recurrent. Recurrent means that I'm able to get from I to itself. Yeah? There is a way from I to I. So if I start at I, eventually I'll be back at I. So there has to be a way from I to I. Okay, so this says that I is an S. And secondly, S is a communicating class. Why is this? Well, let j be an S. Then what you have is a recurrent state I, and from that recurrent state I, you can reach j. Now, by the last theorem, so by theorem 329, j is recurrent. Yeah, j is also recurrent. That's what the theorem says. We don't need this, but what we need is that you can reach I from j. Yeah, this was the second assertion in theorem 329. So this shows that the j in S are such that they can be reached from I, and you can reach I from these j's. Yeah, so this is a communicating class. Yeah, by construction anyway, I'm not missing out any state that you can reach from I, and I and j communicate for all j in S. So this shows that S is a communicating class, and 1 and 2, so the fact that I is an S and S is a communicating class, imply that I is significant. And that's the end of the proof. this is the end of section 3.4. Let me summarize. So you got to know quite a few new notions for Markov chains. A state is reachable from another state. Two states communicate. What is a communicating class? What are absorbing states? What are insignificant states? And with the help of these notions, we could show the main theorem, theorem 329, which said the following: if a state I is recurrent or transient, then the whole communicating class that contains the state is recurrent or transient. Okay, so recurrence or transience are phenomena that appear on the whole communicating class. Yeah, so it's not only one single state that is recurrent or transient, but all the states that are nearby in a certain notion, in the notion that they are in the same communicating class, they share this property. Okay.